Good morning, eighth graders. So this is your 8.6.0 notes about earthquakes and tsunamis. These are probably some of the more destructive sort of catastrophic events that we're going to be talking about simply because earthquakes can happen almost anywhere. Yes, typically around boundary lines, but sometimes we get them even over here in North Dakota. Um, and unlike volcanoes where they have a lot of periods of rest and things like that, or you can truly build away from an active volcano, um, building away from active earthquake zones, not so much. So we're still working with Middle School Earth Science Standard 2-2 and 3-2. And basically, by the end of this, you should be able to explain what causes earthquakes to form and where. But we're still talking about constructing an explanation based on evidence for how geoscience processes have changed Earth's surface at varying times and spatial scales, as well as explaining what causes catastrophic events, and then using those like bits of information to um, predict and mitigate future events. So how can we potentially resolve the amount of casualty or destruction and things like that? Sorry, Will is still sleeping. He didn't have a great night, so I have his monitor. So that's what I just turned down. I apologize. So make sure you have these notes in front of you and let's get going. So earthquakes. Very, very simply, if we're going to talk earthquakes, it is just a vibration in the ground that results from movements along any sort of faults. Okay, and we know faults from our geoscience processes unit as the break in Earth's lithosphere, where one block of rock moves toward, away from, or past one another in a slip, normal, or reverse sort of motion. Essentially, it is either the movement of divergent plates away from each other, convergent plates toward each other, or transformative plates against each other. Okay, so this picture is honestly a really great sort of explanation, but very exaggerated. Um, so you can see simply you got your town here, you had your fault, this one moved down, this one moved up. This is where all of the grumbling started, and it just radiated out, causing for some vibrations or an earthquake. Typically, we're going to see earthquake formations around plate boundaries. So this is when force applied to rock blocks, we're talking plates, can be seen along plate boundaries. So this picture here shows this is all the earthquake activity that is happening around. And you can kind of notice that they're falling along where our plate boundaries would be found right now. So that the size of the dot equals the magnitude. So the larger the dot, the larger the magnitude, meaning more of the shaking and whatnot. Okay? So it's so annoying. I'm going to be 100% with you. That when we talk earthquakes, we're still talking about plate boundaries, but yet we give them different names. Okay, so this is just because if you do any of the reading or a part of the video notes, this information could come to you in this manner rather than the terms we've been using. So there are 3 different types of faults. Okay, we have our strike and slip, we have our normal, and then we have our reverse. So strike and slip, simply put, is a transformative plate boundary. It is where, sorry, I'm gonna get my hands a little closer, where if you think of your knuckles, they kind of strike together and slip past one another. That's what causes earthquakes. So it's two blocks of rock that move horizontally past one another in the opposite directions. So one going up, one coming down, that sort of a motion. Okay, so that's your strike and slip. Now, why normal? No idea. Okay, but normal essentially is that divergent plate boundary. So this is where forces pull two blocks apart, and the block of rock above the fault moves down relative to the block above it. That doesn't truly matter. Okay? Yes, you should understand these pictures. You should understand these definitions just because they're going to help you on the check-in, but it's essentially just moving apart from one another. Okay? Typically, when they do pull apart, you do have one kind of like, I don't know how to show this. You do have one kind of slide down versus the other one. That's all relative. It's a divergent plate boundary. Okay? And then reverse is just the opposite of that. So if normal is pulling apart, reverse is coming together. So convergent plate boundaries. So these are forces push two blocks of rock together. The block of rock above the fault moves up relative to the block of rock below the fault. Okay. We would think that that is like, oh, subduction, but really, even when you have two plates coming together, you do have one kind of taking a little bit more of the lead than the other. Okay. Reverse is where you have coming together. So I think of it, so strike and slip, I got nothing. That's just, you have to know that as transformative. Normal would be building, not destroying. So normal is a divergent because we're building new crust. Okay. Reverse would be the destruction. So coming together and destroying crust. That helps me remember these a little bit better. Hopefully they help you, but hint, hint, wink, wink, nudge, nudge, you're gonna want to know these, okay? At least for the check-in. Okay, there are a couple like parts to an earthquake that we really need to have a good understanding of. And that would be our focus versus our epicenter. Okay, because when reporting on earthquakes in the news and things like that, they interchange these and they're so wrong. So, um, as we know, when a rock moves along a fault, they release energy. Okay, we see this in the form of vibrations or waves. So the waves, we actually call them seismic waves. So these are a little out of order. So if you're looking at the bottom, okay, so seismic waves, these are vibrations on Earth's surface and within the crust. Okay, we can see, let me grab my little pointer, we can see that everything starts here and then the waves move out. It's just like when you drip one little droplet of water into a pool of water or a puddle or whatever, and you have those rings that go out. Okay, that's exactly what is happening with an earthquake. Okay, so your seismic waves and they move outward. Okay, now the focus versus the epicenter. So your focus is where the waves originate. This is deep within the Earth's crust. So the focus, where everything starts, you focus in on, is in the crust. Okay? Earthquakes don't start on land. Okay? It starts within it. So that, and then the epicenter is if you were to follow this straight up, the epicenter is the location of the focus on the surface. Okay? So people talk about the focus of this earthquake started in Tokyo, Japan, or whatever. No. Okay. The focus started hundreds of kilometers below Tokyo, Japan. The epicenter is in Tokyo, Japan. It's on the surface right there. Okay. So seismic waves are the energy that's released. It all starts at the focus. But if you go straight up onto Earth's surface where we stand at the epicenter. Okay, hopefully that helps a bit. Now, the waves that are being produced are actually three different types of waves. So we have P waves or primary or pressure waves. We have S waves or secondary or shear waves. And then we have surface waves, or as this diagram calls it, Rayleigh waves, Riley waves. I don't know. We're just going to refer to them as surface waves. Okay. So it releases these three types of waves. Okay. And it's very important to understand the difference of them because this is how we are actually able to determine what the earth is made of, like deep down inside. I had a lot of questions during structure of the earth, like, oh, well, how do we know it's liquid inside here and it's not solid and da 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 da. This is how we know. Okay, so let's start with P waves. So we're starting at our focus, and then these waves get like pushed out from this event. The first type of wave that is being produced and detected are P waves or primary waves. Okay, these compress and expand like an accordion. That's why they're called pressure waves. You put pressure and you release pressure. Okay, they travel the fastest. Okay, and because of the way that they move, pressure waves can actually travel through both solid rock and liquid rock. Okay, we're able to see this in kind of water models. So not exactly the same, but we can see this in water models to where they are able to travel through the liquid and solid versus our secondary waves. Okay, and obviously because primary first, they're the first to be recorded on our seismographs. Okay, so that is pressure waves. Okay, they compress and expand like an accordion, travel the fastest, and go through solids and liquids. Now, S waves, or secondary waves, shear waves, however you want to remember it. These are side to side or up and down motion. So this is like what you think of with a wave. Okay, they travel much, much slower because instead of just coming together and kind of like flinging apart sort of a thing, they take their time. Okay, so they are slower than P waves, but they're faster than surface waves. They are the second wave typically to become detected on a seismograph. And because of the way they move, they can really only move through solids. Um, so that is why we're able to tell like there is liquid at one point in time within our Earth, because as we detect these sorts of waves, we always find the primary waves, but we don't always find the secondary waves. So that. And because of the way they flow, okay, you got to kind of think if you're sitting in a chair and someone is just like pushing you back and forth, like you're not going to really move a lot. Okay, so just like going like this, not going to move a lot. You just kind of like shimmy your way down. Now, surface waves, if someone is like lifting the back and the front at different times like this, you're going to be moving around a lot. So S waves can actually cause more destruction and more damage than a pressure wave can. Finally, surface waves. So surface waves travel only along Earth's surface. So these are the slowest waves. They're the last waves typically to become detected. But because they're traveling the way that they do, they kind of fall within both that pressure sort of wave where they're slowly, like they're quickly moving across like linearly, but they're also kind of following the S waves to where they do this almost like barrel roll. Okay, so I don't know. This might be a goofy way to think about it, but this is just where my brain goes. So when I think S or P waves, I think more like that zigzag. You have that compression and that release. Okay, if I was to draw it like that. S waves is like woo, okay, that sort of thing. Versus when I get to surface waves, it's like you're doing all of this and like you can kind of feel the like, oh, sort of a thing. I don't know. If it helps you, great. If not, just ignore how ridiculous your teacher is. Okay? Um, so let's erase this in case we don't need 100% evidence that I'm this crazy when I think of things. Um, but yeah, so these are the three types of waves, and it's important to understand that we do have these three types of waves because this is how we determine where earthquakes start and um, all of that kind of stuff. So where the focus and the epicenters are to determine strength and all this to like let others know like, hey, we might have an issue coming our way really quickly. So this is, I feel, a really great, um, better explanation of like you can actually see how these waves are moving and how it can cause the amount of damage that it does. So take a peek at those little gifts. And then this is how we're able to tell what the earth is made out of is because when we have an earthquake occur, okay, we feel it at the epicenter, and you can have seismographs picking up slight readings over here, 90 degrees away from the actual event itself, but you can also feel P waves getting picked up on seismographs directly across the earth from us. So that is how we have been able to determine that there are certain waves that are able to be detected. Now, obviously, we have shadow zones because with the earth being round, you have some deflection and all this or whatever. It's not perfect. But this is how we have been able to tell the difference in earth structure. So, kind of a fun factoid, bringing it full circle from when we started with plate tectonics. Okay, so this is the end of whole group. So I know that we're at 17 minutes, and I'm sorry about that. These are slightly longer notes because we do have all of that information and understanding of the different waves. But this is going to help you in your next steps throughout this unit. So thank you for bearing with me. If you are continuing with lecture, let's keep going. If you are going to go to any of the other note options, you're good to go. Please remember your champ's expectations if you're doing this in class and I'm not present. And yeah, so awesome. Lecture, let's keep moving. So, seismologists, these are the scientists that are studying earthquakes and how they happen, where they happen, what sort of destruction, are we able to start predicting them? All of this. They are kind of big deals in the earthquake world. They use specific tools like a seismometer, and a seismometer records and measures the amount of ground motion um, and picks up like the detections, whether it is more localized or whether it is transcontinental. And then you have a seismogram, which is the pictures over on the left-hand side that gives you a illustration of what the seismic waves are doing in all this. So those are the tools of a seismologist. So the process in which we determine the location, because obviously the focus is deep within the earth and it is felt for miles or kilometers. Um, so what we do to determine where this actually originated from is called triangulation. Okay, so we're looking for the triangulation of the epicenter, and then we know straight down from there, depending on the magnitude of the earthquake, determines how deep the actual earthquake was. So, first things first, to do triangulation, you must have a minimum of 3 seismographs. Okay, 3 seismographs worth of data. Okay, guys, triangle. Three sides, three corners, all that fun jazz. Triangulation. So if you think of like, oh, I'm going to trace this call. The call has to ping off of three radio towers. Da, 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 da. Same concept. Actually doable, I believe. I don't know. I'm just talking now. So to determine the difference between the first P wave and the first S wave is lag time. So obviously we know P waves travel much, much quicker than S waves. So once a seismograph picks up that first wave, you essentially start your timer. Okay, and that determines roughly, thanks to math and linear graphs, we are then able to determine roughly how far away the seismograph was from the potential epicenter. Okay, so we feel it like here at station 2. And then we count the lag time in between the P wave and the S wave. And it determines that the seismograph itself was about 4,000 kilometers away. Okay, so that gives you this whole radius. Anything where the green touches, the epicenter could be. Okay, then using a linear graph to plot the intercepts, you point points of lag time on the y-axis and where it lines up with the distance of the epicenter. Okay. Yeah. Oh, excuse me. Sorry. So that then you plot on the map, you draw a circle using the radius, and then you have to do the same thing from 2 other locations. Okay, so we're sitting here at station 2. We determined that the epicenter occurred 4,000 kilometers away from where we are presently at. But station 1 determined that where they are, it is only 2,800 kilometers from where they're at. So they draw their circle. And then we notice, okay, we have some intersection here and intersection here. So we're getting closer, but we still have 2 options. Okay, and then we check with station 4 and they're like, oh, we didn't feel nothing. We're like, oh, okay, so maybe it's out this direction. Station 3 determines, oh yeah, no, with the lag time, we're sitting at 1,800 kilometers. So they're 1,000 kilometers closer than station 1. So we draw this, we draw our circle, and we're like, okay, well, where all 3 meet, that must be where the epicenter is, because if we all 3 felt it at different times, then it must have been somewhere in between all 3 of us. Okay, that's how we do triangulation. It is graphing, it is math, it is all this, and it is so cool to think of. So this is just kind of like what seismographs are seeing. So we pick up the initial P wave, okay? And this is not always super duper noticeable depending on how far you are from it. And then to the S waves where we can see we got some more like grumbles happening. These are your surface waves that finally catch up to all of it, okay? So this time determines how far we are to where then through math and all this fun jazz, you plot it here, you find the slope, and then you plot your, like where your slope came in, you plot and you draw your circle. And then you hope that 2 other epicenters were able to be, or 2 other seismographs were able to feel this one epicenter. Okay, so that's just kind of visually what is happening. When we talk about the severity of an earthquake, we are talking about 2 different scales. So let's keep that in mind. The first one, which is universally used to determine magnitude, is the Richter scale. And essentially what the Richter scale is determined is the amount of ground motion at a given distance. Okay, so it starts at 0 and there is no upper limit. Now, mind you, We have yet to feel anything over a magnitude 9, but we are aware that the Earth can be so much more powerful than what it's given us thus far. Okay, so it starts at 0. Seismographs can't actually pick up any data though until it's about a 2.5. So ones can be happening all the time, twos could be happening all the time, but we can't feel it at the surface level, and our seismographs are not responding to it at that level. So with each increase of 1, so moving from 0 to 1, it correlates to a 10 times of the amount of ground motion. Okay, so from 0 to 1, it's like 10 powers. Okay, from 0 to 2 would be like 20 powers. Okay, then we keep going, just all of this. So moment magnitude is kind of what we're looking at. This is the exact initial point of energy release. So where that slip actually happened. And then the units on this scale are exponential. Again, we don't know what the Earth truly can do at this point in time. Moment magnitude, each increase in 1 on the scale is equal to like 31.5 times more energy. So a magnitude 8 releases about 992 times more energy than a magnitude 6. So that is a significant amount of energy at the actual epicenter itself. And we have experienced only up to 9. So if you take 31.5 to the 9th power, like that's what we're looking at. I'm not doing that math because you don't need me to embarrass myself. So when we are reporting on earthquakes, you're going to notice that everything is a magnitude something, a magnitude 5, a magnitude 2, whatever. That is the most universal scale that we have for the entire world. The other scale that we use is called the modified Mercalli scale, which measures the the earthquake intensity based on descriptions of the earthquake that people give. And there's a lot of flaws to that. So earthquakes affect people and structures very differently, but also structures are built differently depending on where you are at in the world. How we would experience a magnitude 2.5 would be much, much different than how someone in California would experience a magnitude 2.5. So there's a lot of flaws with that, and we'll get into that here now. So the discrepancy with that is that we have to understand that the modified Mercalli is really going to be dependent and aimed more so toward wealthy countries in areas of earthquakes. For the pure fact of they have the finances to invest in their infrastructure and their preparedness. So when we think of a magnitude 7 earthquake hitting places like Japan, yes, there's destruction. It happens way more often than we'd like to admit. But the amount of damage to their infrastructure is going to be much, much more limited than the magnitude 7 that hits Haiti. Okay? Japan has the infrastructure to support, and they've put like many, many years and intelligent minds into building their cities and their towns to be more earthquake proof, rather than say Haiti, which is a very underdeveloped country because it doesn't have the same money, it doesn't have the same capacities in order to be more earthquake prepared / proof. So the modified Mercalli goes from like a 6 being really strong to a 10 being extreme. Um, and if, like I said, Japan and Haiti were both to experience a 7 magnitude earthquake, um, Japan might rank it as a 7. Like it was very strong. There was notable damage to buildings. Um, there was some well-built structures that maybe like fell, things like that. But a 7 magnitude earthquake in Haiti could have been extreme, where all of their buildings were destroyed. People were cut off from necessary um, like resources, things like that. So that's why the modified Mercalli is not necessarily worldwide used, because it really depends on where you're at. Even in, like I said, if we go back to the example of a 2.5 happening in Los Angeles versus a 2.5 happening here in Fargo, North Dakota, we don't build our buildings the same way that they do in California because the likelihood of us experiencing an earthquake slim to none. So if we were to experience what is really, really chill of an earthquake, we might be like, oh my God, this is horrible. To where Californians might just be like, oh, it shook for a second. We're good. Like, don't even ask us. That was lame. Um, but the second part to why there can be such a discrepancy is because as like psychologists have learned, firsthand accounts are not that accurate. When we go into fight or flight mode, the way your brain perceives something being happen, like actually happening versus how my brain perceives it, so much different. So, yeah, that's why we don't use the modified Mercalli very well or very often. And if we are, it's typically within the same country. So, yeah. Earthquake safety. Oh, sorry. It is like 5:50 right now. So I've been up for about an hour or almost 2 hours. So, yeah. Anyway, earthquake safety. So this is good to know. This is something where like even when Mr. G and I like had that earthquake warning while we were in Japan, um, I really wish I would have remembered this just so I maybe didn't freak myself out as much as I did. But anyway, earthquake safety. So if you're inside, stay inside. Okay. Um, Earthquakes come on so suddenly and can be a very like intense situation. It's just easier to kind of stay where you are at. You're less likely to get injured because you're not then you can get yourself in a part of the room where you're like, okay, I can hide underneath my desk. I can get under my bed or the dining room table, things like that. I can protect myself to where, God forbid, something were to fall. Hopefully, I'm only walking away with some scratches and bruises. Try to move away from any glass, that's supposed to be hanging objects, bookcases, or large furniture that could fall on you. In California, you are required to um, tie any large pieces of furniture to your walls and all of this. Like, you can do that now here in North Dakota. Like, we did that when Will was little with his dresser because kids pull on the dressers and you don't want a dresser to topple over on them. Things like that. But anchor, not tie, anchor to the wall. But in California, you need to do this with like all your furniture. So that. And then cover your head. If you are in a high-rise building, move away from the windows. Just like in a fire, don't try to use the elevators. And if you do find yourself in a trapped situation, tapping on metal parts of the structure could get someone's attention. My brain just goes to like all of those drama, like reality shows or whatever, like Grey's Anatomy, and you just hear the like bang, bang, bang of a person, and then they're like half crushed, but they save them and they live a normal life, sort of a thing. Okay. Again, it's too early for me to be doing this. If you're outside, stay outside. Okay. Move away from the buildings, move away from utility lines. You don't need those snapping and being like electrocution hazards. Be wary of where sinkholes may occur. There's this thing called liquefaction that when rock or solid material is vibrated enough, it does actually kind of become like quicksand. So just be aware of that. Stay away from fuels and any other gas lines. And then try to get it to as much of an open area as possible. If you're in a moving vehicle, stop. Don't drive anymore. Stop. You don't know what's going to happen to the very rigid road structures that we have. So if you just stop your car, the likelihood of you like being okay is going to be much, much better. So just stop quickly and as safely as you can. Stay in your car. Again, this is just added protection for you and your noggin. And then listen to emergency broadcasts. Flip to the radio. Don't be like streaming Spotify through your car, but flip to the radio and they'll be giving out emergency broadcast instructions. Then that kind of goes for anything. Okay, so that earthquake safety. Now, after an earthquake, we always have the possibility of a tsunami. And yes, tsunami is spelled weird. But this is a deadly ocean wave that is caused by intense amount of pressure and vibrations. So typically they are caused by earthquakes. They are less commonly caused by meteor impacts, landslides, or nuclear explosions. So if you do have a meteor that comes through Earth's atmosphere and makes contact with our water, the likelihood of a tsunami is slim. But it can happen. Things like that. They tend to have small wave heights relative to their large wave lengths, meaning that they don't get as tall like this, but they are very drawn out, which can then, once it starts to make contact with the shore, that's when we start seeing some issues. Okay, as they get closer to the shore, there's less space for the water to move, so that's when they start to increase. And then the waves can travel up to 800 kilometers per hour or 500 miles per hour. Your cars can't even get that fast, so this is not a good thing. To determine where tsunamis occur. So where can we determine where tsunamis can occur? So to be honest, because of the amount of plates that are kind of found within the like Eurasian sort of zone, it's very common to find tsunamis within the Indian Ocean. Okay, we have the Philippine plate, we have the Eurasian plate, Indian plate, Australian plate, Pacific plate, like everything playing a role. So places like Japan and Indonesia are more susceptible due to just the amount of activity that's happening there. So that plus then you have the Indian Ocean, which is not very large when it comes to like how big other oceans are, to where we get very intense sort of tsunamis. One of the most notable ones happened on Boxing Day which is it's a holiday typically celebrated on the 26th of December, because that's like the day where you're getting rid of all of your boxes and you're starting to pack up Christmas and all this kind of stuff. So back in 2004, there was an earthquake in the Indian Ocean registering at about a 9.1 magnitude. So Sumatra, Indonesia was right in the path. It hit 8 different countries and it killed about 230,000 people. As you can see from the top picture is from Boxing Day. you have the earthquake damage, but then you have all that water damage because tsunamis come up onto land and essentially pull everything in. So there. Then there is the 2011 Japan tsunami. After a 9.0 magnitude earthquake struck offshore of Tohoku, um, then we had the amount of water to worry about. So 9.0 is already huge, and Japan is very well developed, very ready for earthquakes, especially in their more populated areas, um, to where it caused this massive wall of water. Okay, measuring about 9 meters, which is about 29.5 feet. So taller than most two-story buildings. Um, yeah, so it's it can cause major destruction. You can see in the bottom picture, sorry, I have a dual screen. So you can see in the bottom picture, there is actually levees right here. So very tall compared to where the roads are, to where the water normally sits like down here. But as soon as you get that massive amount of wave and water coming over, like it just spills into the water is not normally above or near the top of this levee. Um, but because of that earthquake, that's what happened to where there were hundreds of thousands of lives lost during that one as well. And that has happened within our lifetime. So, when it comes to tsunami safety, Um, this is important because if you do visit places like Alaska or California, there are always possibilities of tsunamis because there's more plate activity happening over in like the Eurasian side of life. But the waves travel across the ocean. So tsunami safety is important to understand if you ever were to visit California. So you will notice um, a couple of signs before a tsunami actually makes landfall, and that is that there is a sudden rise or drop in the ocean level. So, because of the way waves work, you're going to see water almost kind of recede or go away from the shore. Um, and that you like if it goes out a couple of feet, it's very noticeable. You are to run the opposite way. Um, so you're going to see that drop. Sometimes you see a rise in water where it starts to come up a little bit more, and you're like, why? Why would it do this? So again, run the opposite way. Um, the best thing that you can do for tsunami safety is to move to higher land or higher elevation and to move as far inland as possible. Tsunamis are not just like going to the wave pool at like some sort of amusement park. It is serious stuff because not only is it that moving water that's coming in 500 miles per hour, but all of the debris and junk with it, or it picks up along its way inland. Um, so it's not something you can swim through. Um, and most of the time, you're not swimming through pure water, you're swimming through this gunk, which is just heavy and doesn't flow as nicely, but it does flow. So just be careful of that. So move to higher ground, move inland. Don't think you can take this on like Splash Mountain sort of a thing. Um, so yeah, so those are earthquakes and tsunamis. I know that this was a little bit of the longer sort of notes, but there's a lot of information that we need to understand before moving into a couple more parts of this unit. So if you have any questions, please feel free to reach out to your teachers. We are here to help. Um, and yeah, let me know if you need anything. Thank you, 8th graders. Have a good day.